First of all, let me introduce myself. So who am I? Why am I here? My name is Wynn, and I work as a data scientist at AppNexus. We're an advertising technology company headquartered right here in New York City. We are hiring, in case you're wondering. I work on our inventory quality team. So my job consists of finding good traffic that's on our ad serving platform and removing bad traffic from our ad serving platform. And in my spare time, I like hiking, chocolate, and researching and fighting fraud. Now, why am I here today? I'm here to talk to you about Spark streaming and to share some of my learnings from my journey thus far. One of my goals today is, if you've never worked with Spark before, I want to give you all of the building blocks you need to start playing around with and prototyping your own Spark streaming application using PySpark. I am going to preface by saying that my talk focuses on implementing Spark streaming as a technology and less on whatever machine learning algorithms you decide to apply to your data. And I can't really guarantee that 25 minutes is going to be enough to achieve the world domination promised in that truncated title slide, but I'm pretty sure it's a good first step. And you can trust me on this because I'm a data scientist. I've run the numbers. All right. First of all, what is Spark? So just a show of hands. How many people have heard of Spark, heard good things, hopefully, about Spark? Okay, that's great. So almost everyone here has heard of it. But what exactly is Spark, and why has it become so popular recently? Well, Spark is a cluster computing platform. It actually began in 2009 as a project at UC Berkeley before becoming an official Apache Software Foundation open source project. And the first release of Spark was in 2014, and it's gotten a lot of attention since, especially in the data science world. There are many APIs that you can use to interact with Spark. The one that I'm going to be focusing on is Spark's Python API, or PySpark. Now, why is it that Spark is getting so much attention, at least in the data science world, probably also in the software development world as well? Well, one of the reasons is it is very fast. So with Spark, your computations run in memory. This means you can avoid a lot of the disk I/O latency that was one of the criticisms of MapReduce. And actually, before we moved to Spark at my company, we did use MapReduce extensively. For transformations, Spark also has a very featureful core engine that calculates something called a DAG, or a directed acyclical flow, of all of your transformation steps. This means that transformations that you apply to your data aren't computed until they're actually needed, and they're done so in a very efficient manner. Secondly, compared to some other technologies, Spark is very powerful. It has a very featureful engine, as I mentioned, and you can take advantage of features such as distributed computing, task scheduling, memory management, cluster management, in some cases, fault tolerance and fault recovery, and much more, all from Spark's core engine. Lastly, Spark is also extremely general purpose. With Spark, you can combine many different types of computation in a single, easy-to-use engine. And at least for someone like me who works more in a data science setting where your main goal is to quickly iterate and test hypotheses, this plug-and-play approach is really great because it reduces the amount of time you spend on development work, and you can also pull in Python code that you've already written that's not necessarily already written in Spark. So given all of these benefits, it's really no surprise that Spark has gained popularity, as this Google Trends search shows. I know this bit is cut off, but you can just take my word for it that it keeps going up gradually over the past couple of years. So when I talk about Spark, Spark is actually composed of a core engine, and several libraries that sit on top of that engine. You have things like Spark SQL, which gives you an SQL-like syntax to query your data with, Spark Streaming, which we'll talk about, MLlib, and GraphX, which is a graph analytics library. Today in particular, we'll just be focusing on Spark Core and Spark Streaming. So at this point, you might be asking, why would you want to consider using PySpark for your streaming applications? I would say that actually using PySpark for streaming is a very good choice because it allows you to take advantage of, on one side, all of the Spark streaming advantages, along with all of the advantages of using Python. So on the Spark streaming side, you have such features as parallelism in data input, To give one example, internally at AppNexus, many of the streams that we consume for our data science work are in Kafka, which is a message broker, and Kafka is pub-centric, meaning if you want to consume messages from a given topic, which is how messages are organized in Kafka, you can spin up as many consumers as you want. So I can have an application that has thousands of consumers, and that won't slow down the publisher for that message topic. You also get the benefit of parallelism in data processing. So one of the big pluses of Spark is it allows you to work with data that's way too big to fit within the memory of any single machine. As I already hinted at, under certain scenarios, Spark has built-in features for fault tolerance and fault recovery. And there are many powerful libraries, both within Spark and within Python, that you can quickly integrate so you can just plug and play and get going. And with streaming in particular, you have the advantage of near real-time processing of your data. And on the Python side, let's talk about some of the advantages here. So first of all, there's ease of use and code sharing. Among all of the data scientists that I work with, some of us know Scala well enough to spin up a Spark application every once in a while, but for the most part, we're a Python shop, right? That's kind of the shared language most people on our team have in common. So when you're working and prototyping and developing a lot of new code, I wouldn't discount the advantages of having a shared language so that your results are both maintainable by other people, but more importantly, from a data science perspective, reproducible by anyone on the team. There's also faster prototyping, which is essential if for most of the work that you're either doing data exploration or testing, as I mentioned, and a lot of your code might never even make it into production because, hey, you have a hypothesis one morning and you just need to test it very quickly and it might just blow up in your face, but that's okay because you're working in Python and that's a quick to iterate in language. And lastly, the ability to integrate existing code, such as like very powerful scientific computational libraries in Python. So I'm going to kind of talk through a use case that we have on my team when we're trying to look for ad fraud. So at AppNexus, we process real-time programmatic auctions for ad impressions online. That means you, as that cat in front of the laptop, every time you load a web page or a new tab in your browser and you see an ad, there's often a real-time auction that goes on between different advertisers to determine who gets to advertise their product to you. And we provide some of the technologies that help support that transaction going on in real time. And we process billions of ad impressions a day. To give you an idea of a sense of scope, the average person, this is like across the entire US, all age bands, sees about 2,000 banner ads a day. It's like in the tens of billions of ads served by a single platform is not like an obscene number. And as all of this is coming in real time, messages and data gets pushed out into our logs, which, as I mentioned before, are streamed in Kafka. Now, my team is responsible for finding whenever someone is trying to do something bad, represented by the little crossed out ad here. So for example, someone might be on this marketplace trying to sell something as something else other than what it actually is. Alternatively, maybe that cat isn't a human user that's going to buy a laptop. Maybe that's a bot, and I'm just showing ads to a bot and not getting a return on my investment. There's like a whole multitude of things that we're trying to find. And many times, as these auctions are happening, we see something out of the ordinary with our battalion of machine learning algorithms, and we want to be able to stop it quickly, right? Because sometimes it's just not good enough to wait several hours or for certain data sets up to a day for the logs to be processed and to be populated in downstream databases. We want to be able to find this behavior as close to when it happens as possible so that we can shut it down in a very dynamic manner. So in the use case here, many times we'll have a streaming detection system that takes some sort of anti-fraud action or notifies us or ETLs specific data to downstream systems. And for many of these research-grade applications, we want low latency. That means minimizing the time between when that cat sees the ad and when the streaming detection system of science processes it and figures out whether or not it's something bad that we want to flag and identify. We also want the ability to handle streams of high and variable volume. So there's a pretty predictable time of day and time of week curve to impression volumes online. Understandably, I mean, most people probably aren't logging into their computers to view video ads at 5 a.m., but 5 p.m., you see traffic kind of pick up as everyone winds down work and looks for cat videos frantically. So more ads generally tend to be shown around those periods. So the ability to handle very high throughput data streams that also change in volume. I've mentioned this before, but fast iteration. Many times we'll want to just write code, be able to deploy it, and test the results right then and there without having to go through compiling my Scala code and shipping it and all of that. So that's one additional benefit for hypothesis testing. And scalability and reliability if done right. And no surprise, we've found PySpark streaming to be a very good solution for this. Now that I've kind of briefly sketched out a use case for streaming, I'm actually going to take a step back and talk about Spark architecture. And I'm doing this because many of these concepts are actually going to be extended by Spark's streaming API. So here you have kind of your picture of a canonical distributed app. You have your driver. You have a cluster manager. At AppNexus, we happen to use Yarn. And then you have all of your workers. So these are separate machines in your cluster that do much of the actual work. And for Spark, you're going to need something called a Spark context. And your Spark context is what allows Spark to communicate to the driver, and it's also responsible for coordinating tasks between your driver and all of your different executors. Your executors in Spark are just the different parts of your distributed application that are running on your worker nodes. Each of these executors will be doing something different. Now, in PySpark, it's pretty simple to create a Spark context, which you will need if you are building a Spark application to take over the world. You simply import Spark context from PySpark, and as you can see, it's a one-liner. So sparkconf.setMaster, that part just allows you to specify your cluster manager, and here I named my app foo, but you can name it whatever you want. Now, another Spark programming abstraction that's quite important is one that allows you to handle data input and manipulation. And in Spark, this is called the RDD, or the Resilient Distributed Data Set. Resilient because it's distributed and, in many cases, if you choose to, duplicated across all of your executors. This means that in certain scenarios, let's say the executor on the bottom just decides to go on vacation, has a brain fart, whatever, and it dies, your entire Spark application doesn't come crashing down with it. And it's distributed because all of the data is spread out across all of your nodes because your data set is way too large to fit in a single machine. And you can kind of just think of this as a collection of items that you can operate on in parallel. So in PySpark, you can create an RDD by using Spark context.parallelize, and then you pass in whatever data input of choice you want. Here, it's just an array of numbers. Now, let's see, what's next? Oh, excellent. We get to the meat of the programming. There's nothing interesting here. It just says batches of process data and an arrow. So just in case you think you're missing out on anything important, there's nothing there. All right, let's talk about how Spark handles streaming. Spark handles streaming with something called a microbatch architecture. And what that means is, given a continuous stream of input that's on your left, so it could be messages from different topics in Kafka. You could be streaming data from Flume. There's also support for HDFS and S3, Kinesis, and Twitter, which we'll be playing around a little bit with today. But given that continuous data stream, what Spark does is actually chops it up into smaller batches of input data. And you can think of each of these smaller batches as a little baby RDD, if you will. You can still perform many of the parallel computations that the original RDD allows you to, but this allows you to process it for every single batch. And this entire collection of small batched RDDs is called a D stream, or a discretized stream. So that is how you handle data input in Spark Streaming. And in order to access this and other functionality, you extend your Spark context with something called a streaming context. So, all right. To summarize, here's what's different between a plain vanilla Spark application and a Spark streaming application. And hopefully, like this example will also show you, if you have a Spark application and you want to modify it to play with a data stream rather than a static data set or set of files that you're passing in, it's quite easy and flexible to do so. So elements of your plain Spark application, you need a Spark context, define some sort of cluster manager and a name. You need some sort of data input. This is kind of just a dummy RDD of integers. And you need to define some sort of transformation or computation for Spark to perform on this RDD. I mean, you don't have to, but that's kind of the point of Spark. Now, for a Spark streaming application, here's what you're doing that's different. You're taking your original Spark context and you're creating a streaming context. And this is done by passing in your Spark context as well as a batch size. So this batch size is the duration in seconds of one of the RDDs in your D stream. And you'll be able to tweak that around and do different things with it depending on the specific data source that you're streaming from. You do have to define your data input. In this example, I'm just telling Spark, hey, read everything from port 9999 on this machine and turn this into your D stream. Same as with the Spark application I just showed you, define some sort of transformation. One additional thing that I do want to call out that's different about Spark streaming is you have to explicitly start your streaming context before Spark will consume your streaming data, perform transformations, and spit out whatever output you want. So that is one element that is a little bit different. But you'll get used to it. All right, demo. What are we going to do for the demo? We are going to read some data from the Twitter firehose. We're going to process it using PySpark as D streams, apply some transformations, and hopefully generate some insights and pretty pictures. All right, let's go. I should mention ahead of time that all of this code will be available on my GitHub repo along with the notebook and the Docker file, so you guys can get started with Spark with minimal pain, because sometimes, especially as a noob, setting up Spark was the most painful part of the process. Anyway, so the first thing I'm going to do is run this piece of code. All this does is take my Twitter developer credentials, opens up a connection to Twitter's streaming API, takes every message that gets tweeted in real time, filters out anything that has our president's name in it because it's quite a popular topic. And honestly, I tried other keywords. Nothing was generating enough tweets to actually create interesting pictures and visualizations that I wanted to show you. And then it's taking all of the text of all of these messages and sending them to port 5555. So bear with me here while I actually run this. Okay, we're going to see if this conference Wi-Fi can handle the Twitter firehose. All right. Okay, can everyone see bigger? All right, I'll assume everyone can see. The first thing you'll need to do is to import all of your dependencies. And then what I'm doing here is initializing my Spark context. So one caveat, you'll notice that I have not set a cluster manager to this set master method here, and that's because for the purposes of this demo, it's not running in cluster mode. So sorry, many of the benefits that I just tried to sell you guys on aren't actually going to be here. It's just running on 2 cores of my container. And then all I'm doing is initializing an SQL context, which will allow us to query the results of our data stream. And here, I'm initializing my Spark streaming context with 5-second microbatches. There's no scientific reason that I'm using 5 seconds, just because I thought anything longer and we'd all be very bored. Awesome. Now let's do some data processing. So for this, I'm going to be using the affective norms of English words dataset. This is a research dataset of English words that have a mean score for valence, arousal, and dominance. So these are different aspects of sentiment, like whether or not a word is considered to be good versus bad, active versus passive, strong versus weak. And all I'm doing here is loading my data, and once that's loaded, you can query different words like grin and horse. Now, here's the interesting part. This is where we're defining our streaming data input. And all I'm doing here is telling Spark, okay, listen on port 5555, because remember, that was where the piece of code I just ran is sending all the messages. So if it listens on any other port, it's not going to get anything. Here, I'm just applying a simple window function. This window function takes 10-second intervals and just takes the last 2 5-second batches so that you can see kind of change over time without some of the abrupt cutoffs that can happen if you're just looking at batch. All right, here's my actual data transformation. Let me see if I can. All right, so this line's object here is just my data stream. I am doing a flat map, so I'm taking all of the Twitter messages that come in, splitting by spaces, and returning just think of it as like one flat array of all of the words contained in all of those tweets. I'm filtering out anything that's not in my data set or in the set of English stop words. And for every word that remains in this D stream, I'm performing a map function to return a tuple of the word, and then the average arousal and dominance score for that word, along with a 1, so that I can count. And then for each of the RDDs in my D stream, I'm converting it to a Spark data frame and then registering it as a temp table. You don't have to do this last part. This just allows us to query the data as a table called tweets using the SQL context that I pointed out. So let's run that. And you'll notice if you look at your Spark UI and if you look at where the Twitter stream is supposed to be printed, nothing's actually going on yet because nothing happens until I start my Spark streaming context. So now that that's started, there we go. All the Trump tweets are coming in real time. All right, let's hurry through this while this is still going. All right. Now I'm just going to do a quick visualization to demonstrate. I'm just taking every batch of my data, grouping it so that I can find the most popular words with the sentiment score, and then I'm plotting it on an arousal versus dominance axis. So let's see what shows up. There's always something different in this data set every day, just depending on what's trending. It's very interesting. All right, so, I should take this time to point out some interesting parts of the Spark UI. So, let's see, it's like this smaller. In the Spark UI, you can actually see your batches in real time. So this is a really good tool for kind of debugging your jobs, debugging whether or not your memory allocation is appropriate, and seeing how big your batches are. All right, batches are coming through. Yes, and data is coming through. All right, let's see. For this batch, top sentiment-related words: respect, health, people, news, cut. And this is your pretty picture. Okay, next batch, health, respect, house, crisis, cut. I can see healthcare is probably trending right now. Health, people, house, news, sick. Okay, so as I mentioned, not the brightest and happiest topics to be talking about. As I mentioned, 5-second batches aren't super good for seeing really interesting trends and effects. So one of the things I did was I ran this the other day. This is with a 10-minute batch, so many, many more tweets in your data set. And what I did was I took the entire fire hose and split tweets up into tweets concerning cats, tweets concerning Obama, and tweets concerning Trump. And as you can see, based on the size of the bubbles, even though these sentiment words cluster in different places, many more people tweet words about cats. So I don't know, maybe cats just trump presidents. Another very interesting thing you can do is this was streaming with 10-minute batches for popular New York City hashtags. And generally, the same hashtags will bubble to the top. And every once in a while, you'll get a batch where I guess people are stuck on 278, or they're stuck on the bus, or they're stuck on the subway, but you are gonna see that hashtag just shoot up in that batch, and you can see traffic woes happening in real time. So hopefully I've given you some ideas of why Spark Streaming is so cool. I don't have a car to give away, so I hope I was able to give you some Spark Streaming superpowers to add to your toolkit and show you some ways to use those superpowers. There's my GitHub and email, and with that, I'd like to thank you all because I'm out of time, and may all your streams come true.